Hello everybody, my name is Johannes Kuhlmann from TU Munich Thermo-Fluid Dynamics Group, and today I present to you a top-level parallelization and data fusion approach for identification of flame transfer functions with increased reliability, accuracy and efficiency. The work was carried out by me, my co-worker Shuai Guo and Professor Polivka. Historically, and even today, thermoacoustic analysis was not included in design due to the lack of knowledge and proper methods. Often, instabilities occurred in full-scale tests and are then hard to overcome. So, in order to integrate thermoacoustic analysis into the design process, we need fast and reliable FTF identification methods. We have two approaches available: monofrequent excitation with Fourier analysis and broadband excitation with system identification. The approaches show contrary strengths and weaknesses. One approach is monofrequent excitation with Fourier analysis. It offers high accuracy and low uncertainty, even in the presence of strong turbulent combustion noise. But the results are at discrete frequencies only, and it is expensive to sample the whole frequency band with this method. The other approach is broadband excitation with system identification. In the presence of strong noise, it has limited accuracy except for very long signals, which in turn requires long return times. But it only needs one run for the whole frequency band, and the basic shape of the FTF can be reproduced with short signals. Unfortunately, both approaches are either too expensive, not accurate enough, or take too long to compute. Let's talk about the outline of this presentation. First, I talk about the test case and its LES setup. Second, I show how to parallelize time series generation. And third, I focus on the multi-fidelity Gaussian process, explain its concept, and show an application in an LES of the BRS burner. Let's start with the first part of the talk. BRS is used as a demonstrator. It is a classical swirl burner, which was rigorously investigated in experiment by Thomas Komarek and in CFD by Louis Thévauchon. We use the 30 kilowatt lean, fully premixed operating condition and apply acoustic excitation at the inlet. In this study, the LES is assumed to give correct results. As a matter of fact, our results are in very good agreement with the experiments. Now, let's talk about time series generation. We can run multiple instances of LES in parallel. Here we have two instances. This is the first, and this is the second. Both simulations start at the same initial condition, but with different parts of the excitation signal. The individual output signal must then be merged again. Let's take a closer look. We can run both signals in separate instances of LES. Here you can see the resulting normalized fluctuations of velocity in bottom and heat release rate on top. Signal 1 starts at time 0 with an initial damping of the forcing signal, can be seen here. The same applies to signal 2, can be seen here, which starts with a to later times shifted interval of the original signal. You can see the velocity signal merge after a short transition of 5 milliseconds, round about here. This damping interval is a conservative choice and could be further decreased depending on the stability of the applied numerical method. In the heat release rate plot on top, we can see the start of the second signal here, a short overlapping region in here, and the proposed joint point. The overlap is mainly determined by the impulse response length. After this transition phase, the output signal respects the systematic behavior, as can be seen here, plus some colored noise. This method can be applied to any signal type. Now, let's see how the parallelization approach scales. Our example at the local cluster was computed with 1 second time series length using several parallel jobs. The computations were finished in a short time of only 1 week. This equals a 6-fold decrease in return time. And the parallelization produced only 20% overhead for this case. Let's take a closer look at the return time and what it depends on. The return time depends on the number of nodes, queuing times, workload times, and simulated time per job. On the other hand, the relative overhead is more simple and depends only on total time series and impulse response lengths. Okay, this was good. But can we do even better if we use both signals? In our study, we assumed the LES to be the truth and focused on our data analysis techniques. The high-fidelity results, shown as red arrow bars, are considered the reference within the LES. For our data fusion approach, we need 2 sets of input data. We have a broadband field model in magenta, which we call low-fidelity data, and 6 monofrequent training points, the arrow bars filled in red, which we call high-fidelity training data. Each dataset has a time series length of 150 milliseconds. As you can see, the low-fidelity data is biased and uncertain, whereas the uncertainty of the high-fidelity data is quite low. Please remember, we consider the whole set of monofrequent data the truth, and take a subset as high-fidelity training data. Now, let's talk about the multi-fidelity Gaussian process and how it is done. First, a Gaussian process model is built from the low-fidelity data in magenta. Second, this model is refined by the high-fidelity training data in red in their region of influence with the squared exponential correlation kernel. Here, the most likely output is calculated via maximum likelihood approximator, respecting the variance of both inputs over the whole frequency band. This process is called Gaussian process regression, or short, cringing. Third, we can calculate the uncertainty of the Gaussian process model via bootstrapping. This is a Monte Carlo inspired method where we use different realizations of low and high fidelity training data within their uncertainty range to train the individual GP models and calculate the GP models' uncertainties over the training results. Now, let's see how the method predicts the FTF. The mean predictions of the multi-fidelity Gaussian process, shown as blue line, interpolate the reference results perfectly within their uncertainty range. The uncertainty of the multi-fidelity Gaussian process predictions with 1 standard deviation, shown as shaded area, show a reasonable small uncertainty. Now, the multi-fidelity Gaussian process model is a lot better than the same return time top-level parallelized broadband Box-Jenkins model, shown in green line and green shaded area. The Box-Jenkins mean prediction is still biased, and some of the reference points lie outside of its confidence region. Overall, the BRS-Burner results demonstrate the multi-fidelity Gaussian process excellent prediction of the FTF. Now, let's conclude the talk. We can improve the simulation approach by including top-level parallelization, which decreases return times of time series generation significantly, and therefore renders unbiased SI results reachable. But more interesting, it can be combined with our data fusion approach. Therein, broadband and monofrequent excitation data is fused by a machine learning technique called Multi-Fidelity Gaussian Process, and it identifies the flame dynamics accurately, reliably as demonstrated. And it reduces the amount of data required significantly. So in combination, we get a reliable, accurate, and efficient method, which makes in-design FTF prediction affordable. Now we come to the end of my talk. Thank you very much for your attention.